These are a series of lecture notes that I've made and will make available to my students in general chemistry. And essentially in these videos, I'm just going to read through them, maybe annotate them here and there, and give some context to the notes themselves. Okay, so we're going to start by looking at chemical kinetics. As shown, chemical kinetics is the study of the temporal change in a measurable observable. What do we mean by a measurable observable? Well, anything you can measure and observe. So a measurable observable could be color. You can see a color change. It could be temperature. You can measure a temperature change. It could be a phase change. So you can look at a solid becoming a gas. You can see the solid disappear with time. And you can see the gas evolve with time. So these would be examples of measurable observables. Temporal change just means with time. Another example here is the study of the rate of change of concentrations of substances involved in a chemical reaction. So chemical kinetics measures reaction rate. And we can see that reaction rate measures how rapidly a reaction occurs. And again, we can either look at the reaction change of the concentration or of the products. It really doesn't matter. We'll see in a second that you get the same information. Okay, so factors affecting reaction rates. We can have the physical state of a reactant. So the molecules have to be mobile in order to react. So obviously gases can react very quickly because they're very mobile. Liquids can react very quickly because they're very mobile. Solids react much more slowly because they're less mobile. Concentration, so you can think of supply and demand. If we have chemicals reacting together, we need lots of them to be able to actually find each other once they're mobile. Temperature we'll see later is linked with the velocity of molecules. So you have to be accessible, you have to be able to move. So these items 1, 2, and 3 work in tandem. And we'll see in another video what a catalyst can do. So the presence of a catalyst can also affect reaction rate. So let's take an example. We're going to look at the reaction of A to give B and 2 lots of C. So 2 here just means a molar coefficient. And we have a graph. And we can see that, sorry, I just want to make sure I am recording, very good. So we can see here that we can measure the rate. And it says rate is negative delta concentration of A. Here square brackets just means molarity or molar concentration. Delta T means per unit time. Notice we only have one reactant. The reactant has a negative symbol in front of it, and that's to give us a positive rate. So by definition, or not by definition, I guess, by convention, we want rates to be positive values. So we want rates to be positive. That's just a convention. Now we know that if we look at this slope here, the concentration of, let's see if I can find my, actually I can't find my highlighter. If we look at the concentration of A here, we can see the concentration of A is going down. So that will give us a negative change in concentration. Well, to give us a positive rate, we just get rid of that negative by multiplying through by a negative. So the whole point of this, it just returns a positive rate. Returns a positive rate. Okay, Notice for the products B and C, because they are increasing with time, because the products are increasing with time, they're going to give us a positive rate anyway. So we don't need to make that positive. The other thing I'd like to point out about this graph is the slopes. So notice that the molar coefficient is proportional to the rate. So this molar coefficient is proportional to the rate. So because we have A and B in a 1-to-1 molar ratio, we can see that the rate of decay of A is equal to the rate of production of B. But because C has a 2 molar coefficient, we see that the production of C is twice the production of B. Okay. So I guess I have to clear my annotations as I go. Otherwise, my annotations scroll with me. Okay, so now we'll turn to look at some, this is just a summary sheet of some words that we're going to need in subsequent pages. So reaction order, reaction rate, and rate law. So rate law obviously is a mathematical expression that governs rate. Okay, so that's pretty straightforward, and we'll see a rate law in a second. The reaction order is a component of the rate law, and it's related to several things. It's an abstract concept, but it's to do with the availability of molecules during a reaction process. We can have overall order of reaction, where we just sum the individual orders with respect to each component. And then we can have a rate constant, lowercase k, and we'll see more about that in a second. So for example, if we take a simple expression A plus B to give product C, we can write a rate law here where the rate is equal to a rate constant K, and then we can have the concentration of reactant A to some order, where here M is the order. Notably, N and M and N are not molar coefficients. So these are orders, not molar coefficients. And we'll see that orders must be determined experimentally. You can't theorize them. So orders must be determined experimentally. Okay, so that's very important. So again, this page here was just a summary of some vocab that we'll have to dig into as we start to look at chemical kinetics. Okay, and I want to scroll, so I think I've changed the resolution here. So let's go to read mode again. Okay. Okay, so let's get into some actual expressions now. So I've already said that reaction rate is the temporal change of a chemical process. So let's take this example here, where we have A plus 2B to give 3C plus D. Okay, so chemical A plus 2B to give 3 lots of C and D. We can write a rate expression where for any reactant, we have that preceding negative symbol so that we have, it undoes the effect of the concentration of reactant decaying with time. So minus here because A is a reactant, minus here because B is a reactant. The delta symbol here, the triangle, just means change. The square brackets, A means concentration of A. So we have the change in the concentration of A with time. Notice we have molar coefficients down here. So because there's one molar coefficient of A, we just have one delta T. Because we have two molar coefficients of B, we have two delta T in the denominator. For products C and D, we have a plus sign. Because we have three molar coefficients of C, we have a 3 delta T in the denominator. And again, one molar coefficient of D up here, we have 1 delta T in the denominator here. Okay, so that's our rate expression. We have our rate law, where for the same expression, if we look just at the reactants, and there's no real need why you have to look at reactants, but typically that's what we do. We would have a rate constant, lowercase k, the reactant A to some exponent x, where x is the order. So here, x and y. So we have x and y are orders. We know that we would say it's order x in A. We would say it's order y in B. And we would say overall, it's order x plus y. So overall, this chemical expression is order x plus y. Okay, figure out how to make it stop doing that. Keeps kicking me out of read-only mode. Anyway, interestingly and importantly, the rate expression and the rate law are equal. So here we have essentially the same expression we had above. So we can set them both equal. So if we have a reaction A plus B to give C, then we can have the rate law, which is the rate constant K, A to some order X, B to some order Y. We can also write it as the negative, the change in the concentration of A per unit time, the change in the negative concentration of B per unit time, or the increase in the concentration of C per unit time, but they're both equal. So that's an important point to make. So we alluded earlier that you have to calculate rate orders. So there's a couple of ways you could do that we'll at least look at in this video. So determination of rate law. One method is the isolation method, where you essentially isolate one reactant by making all others constant. So all but one reactant are in large excess, and that's imposed by the chemist. So let's say we have a rate order. Let's say we have a rate law that reads rate is k, a to the x, b to the y. But let's say we want to figure out what x is, and therefore we want to do away with b to the y. We can just make sure that the concentration B is in large excess. So we can just, if it's in large excess, it essentially becomes a constant. And therefore it won't change, it won't affect the dynamic rate change that we need to measure the rate law. So let's see. So if that's a constant, we essentially isolate the rate in terms of a to the x, and we've absorbed, we've altered the rate constant. K has now become k prime, where k prime is now the original k, and then it incorporates the b to the y. So we've just altered the rate constant, or we've absorbed b to the y into a brand new rate constant. So we've essentially made the reaction process pseudo first order. or pseudo. Actually, I probably shouldn't say pseudo first order. I've made it pseudo X order. That would probably be a more accurate thing to say. Pseudo X order rather than X plus Y. Rather than order X plus Y. Okay. And then I could do the same for Y to make it pseudo Y order, etc. Okay, let's have a look now at average rate. So average rate, if we take this example, reaction, nitrogen gas and oxygen gas to give nitrogen monoxide gas, the average rate is just going to be the change in concentration on average per given amount of time. So you can look at the average rate over a short amount of time, a long amount of time, but just the change in concentration per unit time. If we look at the reaction profile for that reaction, nitrogen and oxygen to get 2NO, we can see, again, because it's a 1:1 to 2 mole coefficient reaction, we can see that the rate of change of the nitrogen decreasing and the oxygen decreasing is the same. So here they're being superimposed onto the same curve. And we can see that the rate of change of nitrogen initially at least is twice as fast, or the slope is twice as steep. And you could look at the average at 10 minutes, at 5 minutes, and any increment in between or any increment thereafter. But notice that the average rate really depends on the time that you're interested in. So I would say it really depends on an average over a given time interval. So you could have an average in the first 5 minutes, and you can see the slope here in the first 5 minutes is very different than the slope in the last 5 minutes. So, for example, or i.e., the average over first 5 minutes does not equal the average over the last 5 minutes. So care must be taken. So for that reason, average rates can be open to interpretation and definitely must be interpreted and stated very clearly. So we have to be careful with average rates. Okay, something that is not open to interpretation are initial rates, and for the most part, that's what we will focus on, or we'll at least acknowledge that that's more useful. So initial rates are, in this profile here, you can see that an initial rate would be from time 0. So if you look at the slope here, because the slope of the reaction or the reaction progress changes with time, for different reasons that we'll explore during kinetics, it's a cleaner way to compare different reactions. So initially, we want that initial slope rather than taking slopes at any other point, which we're allowed to do. The slope is going to be the tangent to the reaction curve profile, but we can all agree what initial means. So for that reason, it becomes more useful. Okay, so let's spend a few minutes talking about initial rates. So let's say the rate of reaction is a rate constant, a to the x, b to the y, where x and y are orders. And let's say we've said that b is in large excess, so we've used the isolation method. So we've isolated a, we've made it pseudo x order in a. Then the initial rate, so here the 0 means time equals 0. So the rate at time equals 0 is going to be the rate constant k prime and the concentration A at time 0. So here the subscript 0 just means time 0, but it's still to order x. So if we're interested in this order x, we can use some mathematics to make that exponent a coefficient, and the natural mathematics to use are logarithms. So we use logarithms to bring down exponents and make them coefficients. So we can take, we log both sides of this expression. So we have log the initial rate, log rate 0, equals log of the rate constant, so log k prime. And then because we have a product here, k prime, and then the concentration of A, our log rule says that we add the logs. So we've got plus, and then we also remember to bring the exponent down and make it a coefficient. So plus x log A0. And we can see that that fulfills a straight line expression. So it's a y is mx plus b expression. So we have, if we can plot this as a straight line, we have a plot on the y-axis of log initial rate, and on the x-axis we can have log of the initial concentration, and we can do this for a variety of different concentrations. And then we get the slope is going to give us the order of the reaction. So again, we can determine this, do the experiments, plot the graph, and then determine x experimentally. And then obviously the intercept can give us access to the rate constant. Okay, so now we move to integrated rate laws. And for that reason, we're going to have to just remind ourselves what integration means. So there are many types of integrated rate laws, but there's only a handful of them that we'll need to worry about in general chemistry. And typically they are 0 order, first order, and second order. So we're going to have 3 integrated rate laws plus 3 half equation laws, and then we'll go through them here, and then we'll give a quick summary afterwards. So, okay, so consider a reaction A gives B, simple reaction. So we know that the rate expression is change in concentration of A per unit time. We've just got 1 delta T in the denominator, and we've got a minus sign here so that the negative change in concentration gives us a positive rate. We can set this equal to the first order rate law, which is a rate constant K, and then zeroth order rate law, not the first order rate law. We're looking at 0 order. So it's order 0. So this 0 here doesn't have anything to do with time. It tells us that our order is 0th order. Okay. So we can set these equal because they both tell us the same thing. And then we can just multiply both sides of this expression by -1. So we get the negative sign over by the rate constant here. And then we can essentially pool like terms. So we have a delta A on the left, we have an A on the right, so we can divide both sides by A. So again, we're just pooling the A's on one side here. Pretty straightforward. And then for us to do our our integration, we just want to make sure that this change is not a large change, it's a suitably small change that we can integrate over. So we'll just semantically relabel this delta with a D. So we've got an appreciably small change in A over the initial A equals negative the rate constant per small change in time. And now we're ready to integrate. So we're going to integrate over two sets of conditions. We're going to integrate over final concentration of A conditions and initial concentration of A conditions. So if we look at this A here, the subscript 0 means time 0. That's not to be confused with this superscript 0, which means order 0. So we've got order 0 if we have a superscript. We have time 0 if we have a subscript. So we're going to integrate between those extremes. What are we going to integrate? Well, we're going to integrate our numerator. We're going to integrate between those extremes the change in concentration of A. And on the right side of this expression, we're going to integrate over time. So on the left, we're integrating the concentration change in A. On the right, we're integrating that change as time changes. We can't integrate the rate constant, so we can move that to the left of the integral sign. So that's just a constant negative k. We have the integral between the extremes of time t and time t equals 0, the change in time. Okay. And we actually act upon, we actually perform that integration. And we get this expression here. So if you can't follow that step immediately, let me just add in the intermediate. So this expression here is immediately going to give me the following. So if I integrate between these two extremes, I'm going to get A at concentration T minus A at concentration at time 0. Okay. And that's going to give me minus K. And then it's going to give me T. And then it's also going to give me minus K at time 0, which is just 0. So it's going to give me this. And then essentially, I just take this expression and bring it over here to give A at time t equals minus K t plus A at time 0, which is exactly this. Okay, so that's just the intermediate step. So again, I have a straight line expression where I have on the y-axis, I have A at time t. So if you want to, I didn't in my original notes, but you could put a time t here. We have the slope is negative k. We can plot this against time. And the intercept is the initial concentration of A. To scroll, I have to erase my drawings. So let's scroll down. And again, you can see the initial concentration of A. It will decay with time. And the slope, we can get all of that good information. Okay, so that's 0 order integrated rate equation as a straight line equation. So let's take that straight 0 order rate equation and let's calculate the 0 order half-life. So we start with our first expression. We can then let, by definition, all t's become half of the initial t's. So let's say at t equals t a half, concentration of A equals the initial concentration over 2. So at all times at the half-life t1/2, all the concentrations at whatever time t become the initial concentration divided by 2. Okay, so that's why we can relate this. So essentially this expression here justifies why a at time t becomes 1/2 a at time 0. Again, the t becomes t1/2. We don't change anything to the initial concentration. So then we can bring this a plus, or this plus a0 over to the other side, so it becomes negative again. And then we can clearly see we have 1/2 of something minus a whole of them. Well, that's just going to give us negative 1/2 of something. So let's scroll down and see that. Okay, so 1/2 of something minus a whole thing just becomes a negative 1/2 of something. So we have a negative 1/2 a0 equals minus kt1/2. We can multiply both sides by positive 1 to get rid of these negative signs. And then we can just isolate kt1/2 to give us this expression. And then we can divide both sides by k to give us our final expression for the half-life of a zero-order reaction, which is the initial concentration of A divided by twice the rate constant. Having done zero order, we can do first order integrated rate equation. So consider the same equation, A gives B, but now it's first order, so we can have the rate expression here. I'm going to go a little bit quicker now because it's more familiar. So the change in concentration of A with time is equal to the rate constant K, A to the 1, or A where X is 1, or the first order. We isolate like terms, so we get to this expression here in a very similar way to the zero order process. And then we substitute the deltas for a D, and then we can immediately start our integration process. We're going to integrate between extremes of concentration at time t and time 0 on the left, and between time t and time t equals 0 on the right. But this time we have a denominator because this a doesn't disappear. With the zero order process, you probably guessed that the denominator was 1 because a to the 0 is 1, right? So I don't know how clear I made that. Let me go back, just in case I skipped over that too quickly. Yeah, the reason, so here I've got this a to the 0, it became 1. So that's why I just had one of these, and that's why I just looked at the extremes. But I can't get rid of that denominator in my first order process because it's not a to the 0, it's actually a. Technically it's 1 over a, right? So it's a denominator. So we have this integration rule where we say if we integrate a fraction 1 over x, it gives us natural log of x. So that's just a rule that you can take or leave, so long as you take it. Okay, so we're going to apply this rule for both at and a0. So we'll get a log at minus a log a0. And on the right side, we'll just get minus kt. We're going to transpose, take the minus log a0 to the other side to make it look like a straight line expression. And you can see here, you can either just plot the straight line expression here. This could be a y is mx plus b. Or you can pool the a's back together again using our log rule. So the division of logs, or the subtraction of logs is just the division of the log. So we can see here. So there's a couple of different ways you can plot this. But either way, you can get a straight line expression where the slope will give you minus the rate constant in a way very similar to our zero order rate law. And you can plot these on a spreadsheet and get some pretty nice looking data. So we'll take our first order integrated rate expression and we'll calculate the half-life. So we can take our rate, so from our expression here, I'll take this one here on the left, y is mx plus b expression here. We can, again, assume that at the half-life, all t's become t's a half. So therefore, the concentration AT becomes half the concentration of A0. So if we look at this numerator here, AT just becomes half A0. And so if we look at this parenthesis here, we've got a half of something as a numerator and then a whole of something as a denominator. Well, that just goes into itself 1 over 2. So that just becomes a half. Okay. So we have minus log 1 over 2 as the numerator here on the left. And then, so if this thing over here, let me make this a bit clearer than it's reading. So this goes into itself once, it goes into this guy twice. So that's where our half comes from. And then we know from our log rules that if we take, so if we focus on this expression here, we know from our log rules that if we change the sign of our log argument, we invert the fraction. So this is just because minus log 1 over x is positive log x over 1. So therefore, minus log a half is positive log 2. So we can just say that positive log 2 is equal to kt a half. And then we isolate t a half, and we've got t a half is log 2 over k, and that's our half-life expression. Okay, so that's pretty simple. Okay, so we've looked at zero order, first order, and now the last one that we'll look at in these videos is going to be second order. So we've got our expression A gives B. Same old, same old. We've got change in concentration of AP in a time. That's the rate expression. Rate law, we've got a rate constant, and then A second order. So here it's second order in A. We rearrange, multiply both sides by -1 to get the negative away from the change in concentration. We can now pool like terms. So we bring the A squared down here, change the deltas over to D's in preparation for integration. And now we're going to integrate again. We can't get rid of that denominator, A squared. We're going to integrate again between a final concentration A and an initial concentration A on the left, and on the right, we're going to integrate between a final time t and an initial time t equals 0. We're going to use not a log rule, we're going to use another integral rule that says that the integral of 1 over x squared is -1 over x. So here we've got, that's exactly what we have, where here x is just concentration of A. So here's our integral expression. Here's the rule we're going to follow. So this -1 over x applies to both A at time t and A time t equals 0. So we take time t and then subtract time 0. So we have minus the 1 over x applies to A at time t, and then we subtract the -1 over x again, which returns a positive value here. So it's a double negative, minus minus 1 over x becomes plus 1 over x. And then that equals minus kt, because we have the minus kt, and then we have a 0, so it's just minus kt. Okay, we can exchange these two to make it look a bit prettier. So we've got 1 over a minus 1 over a0. Or rather, I've multiplied through here by negative 1. So all these terms here are multiplied by negative 1 to give this expression here, which you can see if we transpose this minus 1 over a0 over to the other side, we can have again a y is mx plus b expression. We can plot graphs on a spreadsheet, etc. Voila, and we can get access to the rate constant. So that's all pretty straightforward. Okay, and now finally we'll go for the half-life. So we have our integrated rate expression here. Usual at the half-life, t becomes t a half. So a at time t becomes a half a at time t equals 0. So we substitute this term on the left here, 1 over a at time t, with 1 over a half a at time t0. This half in the denominator flips back up and gives us a 2 over a at time 0. So hopefully that is straightforward. This 2 here flips back up and gives us this 2 here. And the t becomes t a half. Okay. So hopefully that was straightforward. And then we've got 2 somethings minus 1 something. Well, that just gives me 1 something. So we get 1 something. So 2 over a naught minus 1 over a naught is just 1 over a naught. And that equals k t a half. And we can isolate t a half to give us 1 over k a at time t equals 0. So we've seen 0 first and second order rate, integrated rate expressions. And again, for the half lives. This slide, you can look at this on your own. I won't go over it too much, but it nicely focuses on the units of the rate constant. These are the units of the rate constant are things that you should be able to interpret. So if we know we need, for example, if we know that in a zero order reaction, the measurable observable or the temporal change in a measurable observable, all the unit must be held within the rate constant because a to the 0 order is just 1. So the unit for the rate constant itself must contain all the rate information. However, on a first order process, you actually have a concentration. So the rate constant doesn't need to hold all of that information. It can just hold the frequency. So here we lose the molarity expression because we actually have an active molarity. So you can go through these, get familiar with these units of rate constant. Why? Because that might be information given in a question, and that might be, rather than a question say, hey, this is second order, it might just say, hey, the units of the rate constant are reciprocal molarity, reciprocal seconds. And if you can't make the link to second order from that, then you would have missed that clue. Here's now a summary of the information that hopefully we've just been through. So we've got, we saw that in all cases, whether for zero order, first order, or second order, we have straight line expressions that we can solve on spreadsheets, etc. We have integrated rate laws for all 3 types of rates. And we also have, importantly, half-lives for each type of rate. So this is a nice summary sheet. Okay, let me just see. So we just have a couple more of these pages to go in this first video. So we're almost done with the first video. So some factors to gear us up for later videos and discussions, some factors affecting rate. So we've looked at, or we've mentioned some factors that might affect rate. We know that concentration can affect rate. Let's see if I can highlight that. I don't know if that will actually highlight. Nope. Let's see if I can highlight. I'm not sure how to highlight that. I thought I could. Huh. So I thought I could highlight. Nope. I guess that's not highlighting, is it? Oops. Okay, I will not try and do that again right now. Okay. So we've seen how concentration can affect rate. We've mentioned that it can. And we know that rate reaction order can affect rate. At least we've mentioned it can. We'll see in subsequent videos how it can. Then, what are the actual procedures by which they exercise their ability to affect rate? So this is what's going to take several more videos to look at. But essentially, we're going to look at collision theory. So molecules are going to collide. Bonds will be broken. Bonds will form. There's going to be exchange of energy. It's a very dynamic, energetic process. So we are going to look at collision theory, but it's not just colliding objects. There's going to be, as bonds form, if we can cast our minds back to previous work we've done in general chemistry, looking at atomic and molecular orbitals and atomic orbitals, we know that the orientation of orbitals is important. So there's going to be orientation factors that will be important, energy of collisions that are going to be important. So collision theory, orientation of collisions, energy of collisions, temperature that can impart energy to a collision. These are going to become important as we move forward. So again, if we know that if we increase the temperature, we can alter the kinetic energy of molecules and therefore increase not only the frequency of molecular collisions, but the energetics of molecular collisions. Activation energy we'll look at in a bit of detail in subsequent videos by looking at the Arrhenius equation and the Eyring equation. But activation energy is the energy needed to exceed beyond just a physical change all the way to a chemical change. And that will be the minimum energy needed to initiate the making and the breaking of the bonds that actually lead to a significant change in chemistry. And these are going to be related, or all this information is going to be packed into that rate constant. So I guess what I will note here is the rate constant encapsulates collision theory information. Details. So we know, or at least we've seen on these slides, on these in this video, how we can do an experiment in the lab. We can plot a graph. We can find, for the most part, that the slope gives us access to the rate constant. And what we need to do subsequently now in subsequent videos is to look at, explore what that rate constant actually means and what's hidden inside it in terms of collision theory. So as we come to the end of this first video, yeah, there's just two more things I want to look at. Seeing as we're looking at temperature and energy, then I just wanted to end this video with a quick look at temperature. So temperature, what is temperature? There's different ways to think of temperature. Remembering kinetic molecular theory, which is the theory of molecular motion, we know that each degree of freedom, according to kinetic molecular theory, has an energy of kBT over 2, where kB is Boltzmann's constant, T is Kelvin temperature, and 2 is the number 2. Where kB, that's what we just said. And in 3 dimensions, we have 3 lots of kBT over 2, which would render kinetic energy in 3 dimensions as 3/2 kBT, stated here. We know if we isolate temperature here, so we bring the 2 over here, we divide by 3, and we bring the kB down here, we can give a definition of temperature, which is 2/3 kinetic energy over Boltzmann's constant. And we know that the number 2, the number 3, and Boltzmann's constants, they're all constants. So 2 over 3 kB is itself a constant. So we know, therefore, the temperature in Kelvin is equal to that constant, which I'll call constant, multiplied by kinetic energy. Or we can say we can get rid of the equal and constant symbol and replace it by a proportional symbol. So this funny squiggle here means proportional to. We know that Kelvin temperature is proportional to kinetic energy. So Kelvin temperature is proportional to molecular motion. We know that kinetic energy is also written as mass velocity squared over 2, which I'll show you in the next slide. Therefore, temperature is not only proportional to kinetic energy, but it's proportional to specifically the square velocity of molecules. So in words, temperature is proportional to the square velocity of molecular motion. It is now easy to imagine how the melting of ice is accompanied by a rising temperature. Increase the temperature of ice, the water molecules in the solid will move quicker, and therefore they will jiggle each other apart and break the interaction between them. Okay, and then just to remind each other, to conclude this video, we said that kinetic energy is also mv squared over 2, where m is mass of the molecule, v is the v is the velocity. Just remind each other where that comes from, because it's important. I think it's important enough to remind each other where it comes from. It comes from Newton's second law. So Newton's second law says the force is mass times acceleration. And we know that acceleration is the change in velocity per change in time. So we can write, instead of a, we can write dv by dt. So we've got force is mass dv by dt. We know that energy has the same units as work. And we know from, I don't know, high school, middle school, I'm not sure which, we know that work is the sum of forces applied over distances. So for example, if I were to move an object over a total distance, the force that I would have to exert to move that object, I could quantify as the work I did. So here we sum over incremental distances dx. So that sum over dx would be the total distance. And then the force over that total distance would be the work done. And I'm looking at work now because I'm looking at the same units as energy. Or if you like, you can say that energy, one way to think about kinetic energy is the capacity to do work. I know, so I can basically sub in now this expression for force into this expression for work. So instead of mdv by dt, I'll stick, instead of f here, I'll write mdv by dt. So here's my m dv by dt. I took the m to the left side of the integral sign because it's a constant and I'm not going to integrate over it. I'm only interested in things that have a change or a d in front of them, which is position, velocity, and time. I can change the order here. And if I change the order like this, if I just exchange dx and dv to read dx and dv like this, I've got dx dt. Well, that's change in position per unit time. Well, that's just velocity. So I can replace dx by dt by the symbol v for velocity. And now I have velocity multiplied by a change in velocity. Well, I know from another integral rule that if you integrate over something raised to the power n, it just becomes something to the power n plus 1 divided by n plus 1. So you can just take that as one of the canonical integral rules. So here I've got v to the 1. Well, that's just going to be v to the 1 plus 1, which is 2, divided by 1 plus 1, which is 2, which is going to give me mv squared over 2. And that's the origin of mv squared over 2. Okay, so that will wrap up this video. And I hope it was clear. And I hope you watch it before you watch the next video.